The next section of this chapter is going to start to deal with statistics. Now, most people have a fairly visceral response to the concept of statistics. They really don't like it. They don't make sense to them. They hate having to calculate stuff. All of it is very negative and very awful. And I was actually one of those people at the beginning because statistics didn't quite make sense to me. But once I actually started to understand what statistics were accomplishing, why we were using them, and specifically what they were looking at and how I could use that, it started to make a little bit more sense to me. So hopefully by explaining sort of some of the why and some of the how, it'll help take away a little bit of that apprehension towards statistics. Or at the very least, maybe you will just take some comfort knowing that I won't ask you to actually calculate any statistics for our midterms. So mostly just applications and looking at things and drawing conclusions based on statistics that have already been calculated. So we're going to look at two broad categories of statistics. We can have descriptive statistics, which are all about organizing and summarizing data in a useful way. Usually you'll see it associated with graphs, something that we can look at and get some meaning out of it. We also have inferential statistics, and this is interpreting data and allowing us to draw conclusions from that data. So inferential statistics would be like allowing us to tell if there's a difference between two groups, like an experimental group and a control group, or something like that. But let's start with the descriptive statistics. So one of the easiest ways to describe data is to focus on some kind of measure of central tendency. And that's a fancy way of saying, where's the middle of our data? Where's the center of our data? And there are three basic ways that we can describe the center of our data. The first of these is the mode. And the mode is the value that occurs most often. So if we look at this diagram here, the mode is indicated by this red line, and it shows what the highest point is. For a diagram like this, we would assume that across the bottom we would have whatever measurement that we're taking. This could be height, this could be IQ, this could be whatever score it is that we're looking at. So our x-axis would be our score of interest. And then across our y-axis, this vertical axis here, that would be our frequency. So the thing that occurs most often is our highest point. So the mode occurs the most often. So that is the mode there. The next is the median. And the median involves looking at the total number of values that we have and divide them in half. So if you have a bunch of height scores, you're going to order them from the shortest to the tallest, and you're going to find the middle of your data. So if you have 11 different scores, to find the median, you would line them up from lowest to highest, and you would find the number that's in the middle. So the 10th score, or not 10th score, I just paused specifically to draw this out because I need the visual representation here. So we have 11 scores. We'll say that this is our smallest value and this is our largest value over here. So then what we want to do is find the middle of our data. So we cross out one on this side and one on that side, one on this side and one on that side, one here, one here, one here, one here. And then we are left with, so 1, 2, 3, 4, 5, 4. Oh, I just can't count is our problem here. So in this situation, instead of having 11 data points, which would have been convenient and useful, we're left with 2 scores in the middle. So our median would be these two numbers. If they're the same number, say that these are both a height of 150 centimeters, then we would report 150 as our median. If they were different, what we can do is add these two together and divide by 2. If, like I had originally intended, there was 11 scores, then that would mean that we could cross out 5 on each side and be left with 1 number in the middle and just report the median as the 1 number in the middle. But either way, to find the median, you basically have to order your numbers from smallest to largest and find the data point that's exactly in the middle of your data. The last kind of central tendency is actually one of the easiest to conceptualize, at least for me. And the last one is the mean. So the mean is simply the average, where you're finding the center of the data set based on adding up all of your values and dividing by the total number of observations that you have. So if you had 10 measurements, you would add up all 10 of your measurements and divide by 10 to get your average value. So the way that I remember these is, for whatever reason it stuck with me from grade school, the average teacher is mean, so the mean is the average. The mode starts with MO and it occurs most often. And then the median is like the median in a highway. It runs right down the middle. So that's how I tell those three apart. Too far? When we're describing our data, the other thing that we might want to describe, in addition to where the center of our data is to describe the variability, which is just going to be some way of quantifying how spread out our data is. So it's giving us an idea of what the shape of our data is. So if you look at this data here, we find that it's actually kind of leaning to one side. We have a long tail on one side. So how would we describe that in terms of the spread of our data? So we can use something like the range, which is where we subtract the lowest from the highest data value. So what is the spread covered by all of the scores that we have? So if we have, we're looking at height still, we would take the shortest height and subtract it from the largest height, and that would give us a range of how many centimeters our data covers. We might also use something like standard deviation, which is a measure of the spread of the data around the mean. The larger our standard deviation, the wider our data will look, the more spread out it will be. And variance is closely related to standard deviation. So standard deviation is that spread around the mean, and the variance is the squared, the average square deviation score. So you take your standard deviation and square it. So usually you'll see someone report either the variance or the standard deviation, and both numbers are fairly closely related to one another, and they're both describing that spread of the data. So if we want to look at an example here, we can see a fairly normal distribution here, but we can see that the shape of the data is slightly different. So the same as with the original curves that I was showing, where we have the score on our x-axis and then the frequency on our y-axis, we have the same setup here. So here we have IQ, and our central tendency is going to be 100, and that's actually a product of IQ. IQ is actually set up and designed in such a way that the average IQ is 100, but that can be relevant later. For this side, we have the number of people who have that IQ, or the frequency of that score. It's not labeled with any kind of numerical value, but the higher you are on this axis, the more people with that score. And so here, the purple line, we can see that there's more spread there. So while both curves, the scores for both men and women, have an average of 100, we see more variability. We see a higher variance with the men's scores than we do with women's scores. So that's us describing the shape of this data. In addition to just the variance, we can actually talk about things like skew. So here we have a normal distribution where our mean, median, and mode all sit very much in the middle of our data. And we see a pretty much symmetrical curve that drops off on either side. When you are statistically talking about a normal distribution, there's a couple more factors that you need to make note of, but for the purposes of this course, that's fairly enough. You can have a bell-shaped curve that's symmetrical, and that's normal enough for us. We can also have either a positive or a negative skew. And the way that I try and remember this is that positive skew points in the larger direction. So it is more positive. And what we notice here is that our mode still occurs at that peak in the middle of our data there. So the mode doesn't move even when we have a positive skew, but the mean ends up being far more affected. It gets pulled out in this direction by outliers. So values that are a lot higher than the bulk of the data. So if this was a height graph, we would have most people have an average height around 120 centimeters. I don't know. I don't have any real data on height. But maybe if there's some people out here who are over 2 meters tall, they're skewing our data in that direction. And by having some large scores this far away, we pull the mean in the positive direction. So the mode is very resilient to the skew produced by outliers. The mean is highly influenced by outliers, and then the median somewhere in the middle. And then we can also have negative skew, which would be that we have some outliers on the smaller end of the scale. So it is more negative, or at least smaller. And we see here that the mean is still pulled towards the negative, it's pulled toward those outliers, and the mode stays right in the middle at the peak there. So just what we would expect from what we saw with positive, but flipped in the opposite direction. Now, we're going to come back to that normal distribution. And our normal distribution is fairly predictable. It looks the same, it has the same properties, and most of our data, though not all, is going to end up falling somewhere in the range of normalcy. And so we can make some assumptions or some estimates based on our knowledge of this normal distribution. So we can actually estimate the probability of observing any given score based on that normal distribution. Within statistics, there's this arbitrary rule that if anything is rarer than 5%, if the probability of an event occurring is less than 5%, we can say that that event is sufficiently rare, it probably didn't occur simply by chance, and then we can be confident that we observed that score, we observed that value because of some factor that we're measuring in our experiment. So some statisticians really don't like this arbitrary rule of using 5%. Sometimes you'll see that people they will propose a different p-value. So usually you'll see p of 0.05. Sometimes you'll see people go more strict and they want, say, 0.01, or maybe they want to be less strict. That you can kind of pick what it is. But for the most part, the standard rule will be 5% probability of an event occurring. If the probability is 5% or less, then we can be sufficiently confident that we observed that score. It is an extreme enough score that it probably happened due to some kind of factor, something that we're measuring with an experiment perhaps, as opposed to having it occur by chance. Now, we don't always just look at frequency distributions, though a lot of statistics are done with frequency distributions. We might want to compare the relationship between two or even more of our measured variables. So we might look at, say, the relationship between an independent and a dependent variable, or maybe two variables that we're measuring, or maybe we're going to go multivariate and look at 3 or 4 or more variables, make it really complicated. If we're doing that kind of research, we are going to be conducting correlations. And so when we're conducting a correlation, we care about the relationships or the associations between variables. But there is an important caveat here, and this is the fact that correlation does not equal causation. So what that means is that we can find that two different factors are related. So maybe there's a positive relationship between studying and the grade that you get, where the more that you study, the higher your grade is. But from just doing a measurement, from just doing a correlational study, we can't say that studying alone is what caused an increase in grade. Maybe students who get higher grades study more because they want to maintain their grades. So maybe it's the grade that causes the studying, or some other factors explaining that. So when we're not conducting an experiment, when we're not actively manipulating one of these variables, we can't make conclusions about causation. We can't assume that one factor is causing or changing another. Now, when we're looking at a correlation, we care about two factors. We care about the direction and the strength of a relationship between our two variables. And again, you can look at more than two, but we're going to keep it at two because that's really easy to display. So we can have a situation like this one in the bottom. So we're looking at studying on our x-axis and performance on the y-axis, and we're seeing a positive relationship. So as you study more, your grade goes up. So again, we can't conclude that the studying is causing the increase in grade, but we can say that there's a relationship where as one increases, so too does the other. And because we're not manipulating either of these, both of these are technically dependent-ish variables. We could have either of these on either axis. It just sort of depends on what you're looking at. We can also have like this one here. So we have grade again on our y-axis, but this time we have how many days you miss in a semester. And so here we have a negative correlation. So as the number of days you miss goes up, your grade goes down. So for a positive correlation, as one goes up, the other also goes up. And with this one, as one goes up, the other goes down. And with this last one here, we're seeing, again, studying and performance, and we're seeing a positive relationship. We still have a line that goes up as both of these increase, but we'll notice that our data is more spread out. So instead of a direction being either positive or negative, this is actually showing us the strength of a relationship. So this relationship, where the dots are very close to the line, is a much stronger correlation, and this one, where the dots are spread out, is a weaker correlation. And I'm going to go through some more specific examples of each of these and talk about them in just a little bit more depth, because I do find that this is a concept that a lot of people struggle to conceptualize. So first off, let's look at a correlation coefficient, and this is a value, usually denoted as a small case r, that describes the relationship between two variables. And so this correlation coefficient will be reported as a number somewhere between -1 and +1. And so from this, the sign indicates the direction of the relationship. So just like here, we had a positive relationship and a negative relationship, the sign in front of our number tells us if it's a positive or negative correlation. Positive meaning as one increases, the other increases as well. Negative meaning as one increases, the other decreases. So that's what the sign is telling us. The absolute value, whether the number is close to 1 or close to 0, regardless of the sign, tells us the strength of that relationship. So the closer to 1, whether it's positive or negative, it doesn't matter. That absolute value of 1, the stronger that association is. So the closer to the line all your dots are, the closer your R will be to 1. So this might be an R of 0.9. It's very, very close to 1. It's a very strong correlation. Whereas this one over here, the dots are very spread out. So this might be an R of 0.5. Sort of moderate strength. But let's actually look at an example of this. I've put a number line at the bottom to help illustrate this. And again, I'm going to go over the topic a couple of times because it is fairly complicated. So our positive correlations are the ones that are larger than 0 all the way up to +1. So an increase in one variable relates to an increase in the other. So the more birds I have, the happier I feel. So our R is going to fall somewhere above 0 all the way up to +1. We might have a negative correlation. An increase in one variable relates to a decrease in the other. So the more work I have, the less happy I am. So it's going to be just under 0 all the way down to -1. We can also have zero correlations. And with a zero correlation, it's an R of 0, we're saying that there is no relationship. So we're saying that our two variables are not correlated to one another. There's no pattern, there's no association between the two. And so we can look at some examples here. We have another example of a positive correlation. As one increases, the other increases as well. We have a zero correlation where you couldn't really draw a line through this data to sort of find a line of best fit. It's just random. There is no correlation. So that's an R of 0. And then we also have a negative correlation. So as one increases, the other decreases. It goes downward. So that's what those look like. Now, we're going to think critically about the pros and cons of correlations. So some of the advantages of using correlational research is that it can actually show you the strength of relationships. So by getting that R value, we can see how closely related two concepts are. And this can be really useful to help us make predictions about different variables. So we can make assumptions. If we know that we have a positive association, we have a nice line, we can actually get the equation for that line. And maybe we've only measured values for a certain span of time. But if we continue that line onward, we can actually make some extrapolations. We can make some predictions either into the past or forward into the future based on the line that we've made from the data that we've measured. So we can fill in the gaps. We can make educated guesses about what might be a score for one variable if we know a value for another variable based on the relationship that we see, which is really useful. And correlations are also really helpful to help us identify real-world associations. So if you don't know what you should start studying, you can start looking at correlations. If X, whatever it is that you're looking at, tends to vary along with Y, whether it's positive or negative, that gives you some indication that there might be something going on between the two of those. So you might want to look closer, maybe conduct an experiment to figure out what's going on. Now, it's not all positives. There are also disadvantages of correlational research. Again, we can't assume that there is causation here. Correlation does not equal causation. We don't have enough information to know that a relationship exists, that a causal relationship exists. Those relationships may actually be to some third unmeasured variable. There might be confounding variables. There might be other things happening that are influencing what we're seeing. So when we have a correlation, it shows an association, but it does not show a cause. So keep in mind that these correlations can be misleading. As a quick example of how this might be misleading, we can look at something like intelligence and birth order. So here we see a negative correlation. So the firstborn has a higher intelligence, the secondborn has slightly lower, and so on and so forth. So is this saying that the order that you're born in determines how smart you are? Or is there something else going on? And in this case, this is a pretty common scenario where we didn't take into account the fact that birth order will also vary along with age. So the firstborn has been alive longer, so they are older. And as you get older, especially when we start looking at children, you will score higher on IQ tests simply because you are older and better able to understand them. So this isn't necessarily saying that the firstborn is always smarter, but this is actually kind of mixed up in with the current age of the children. So we would have to control for that extra variable if we wanted to make some kind of meaningful conclusion here. So we want to keep in mind that there might be some extra variable noted here as Z that might be driving what looks like a relationship between our X and our Y. So the first example was birth order and intelligence. Another example may be that we see a relationship between good social relationships and greater happiness. And so instead of concluding that making or being better in social relationships, by having better relationships, you become more happy. We don't know that that's the case. Maybe being happy makes you more friendly and allows you to form more relationships. Or maybe there's something external, like a personality type, that makes you more likely to be happy and makes you more likely to have more friends. So this is saying that we can't infer directionality, and there may in fact not be a direct relationship between two things that we're measuring. There might be a third variable that affects both of them separately. And that's something that we always want to keep in the back of our minds when we're conducting research. Now, the last slide that I want to cover talking about evaluating research is actually thinking critically about the results that we've gotten. So these are basically things that we want to keep an eye out for. So we want to watch out for things like a sampling bias. So we mentioned earlier on that we want a sample that's representative of our population. If the sample is non-representative of the population, if there's some kind of bias in our sample, then the conclusions that are being drawn aren't necessarily representative of the population, because the sample isn't representative of the population either. So we need to keep that in mind, and that's especially important in psychology, where a lot of the samples, where a lot of experiments are conducted, especially in North America, especially on undergraduate students at universities in North America, and then people try and make conclusions on larger groups, which isn't really a valid way of conducting research. We also mentioned placebo effects, where a participant's expectations can lead them to experience some kind of change based on what they expect to happen. So we want to keep that in mind, and we want to control for that as researchers as much as possible. We also want to make note of distortions in self-reported data. So when people are asked questions, they might answer in ways that make them look better or don't make them look bad. So we can have the social desirability bias, and this is just a tendency to give a socially acceptable answer to a question that's about you. So maybe someone asks if you have voted, and you don't want to seem lazy, so you say yes. We might also have an issue with response sets, and this is a tendency to respond to questions in a particular way. So maybe there's my mind completely blanked there, a controversial question, and you don't want to answer that you agree or disagree. Maybe you want to answer in the middle so as not to anger anyone. So you'd pick a neutral response. Or maybe people would respond, strongly agree to everything or strongly disagree to everything. Those are possible response sets that you need to watch out for as a researcher. We might also see a halo effect, which is where we have the tendency to let our initial performance or liking affect future judgments of performance. So maybe the first time you do a survey, you say that you really enjoyed a topic, and when you come back to it, maybe you don't enjoy the topic anymore, but because you said you liked it, you continue to respond that you enjoyed it, even if your opinion has changed. We also have to consider experimenter bias. So as humans, researchers are also prone to bias. So we might unconsciously influence our recording, our responses, what we're measuring, just by being there. And so we might see influences on our experiments, on the data that we're collecting, based on what we expect or what we prefer, or even just on being present. So researchers tend to see what they want to see, whether they mean to or not. So we tend to find that errors usually occur in the favor of the hypothesis. So if we think that there's an effect between A and B, and we're presented with ambiguous data, we might score it as supporting our hypothesis, even if it could just as easily have gone against the hypothesis. Similarly, researchers might also unintentionally influence the behavior of their subjects. So our body language, the way we ask questions, our expressions, all of that can influence how people answer questions and how they behave. So to combat this, we can use what's called the double-blind solution. And so in this situation, we basically say that neither the subjects nor the experimenters know which subjects are in the experimental and which subjects are in the control groups. So double blind because the subjects don't know what's going on in the experiment and the experiments don't know what's going on with the subjects. So they can't assume that they're seeing an effect if they don't know if someone's in the experimental group or the control group. And this helps us reduce some of that experimenter bias, which is absolutely important when you're looking at research.